This video is going to be a brief introduction to complex ions and ligands. Hopefully after this video you'll gain a little bit more understanding and won't find them so complex. But first of all, we're talking about the D-block elements here. We're talking about the transition metals such as scandium, titanium, vanadium, iron. So we need to be familiar with the electronic configuration. A nice standard 1 or 2 mark question in an exam may be write the electronic configuration of this atom or this ion or a few different ones in a series. So for a generic atom, like I said, this is just a reminder before we go into the complex ions. Structure is 1s2, 2s2, 2p6, 3s2, 3p6, 3dx, 4s2. 4s2, before being filled, it's a lower energy, it's usually around here, but because it's filled, it's now become a higher energy than those d orbitals. We just have to remember that key point here. I've also written X, if this was a 3D metal of course, which is the first row between scandium and zinc, because it can be any number depending what you're looking at. For example, iron is 3d6, which I'm now just going to write. 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. Now what about the iron 2 ion? Well, I'm not going to write out this section again, as it's identical, right? However, it's 3d6, and we've now lost the 4s2, because when you remove electrons to form an ion, you remove the highest energy electrons, right? The easiest ones to remove, which in this case are the 4s2. Both of them are gone. Now what about iron 3+? Well, once again, I'm not going to write that part out, it's exactly the same as above, but we now have 3d5. So we've lost 2 electrons from the 4s2, and we've lost 1 electron from the 3d6. Simple as that. You're losing 3 electrons, you take the highest energy ones first, and then you start working your way through the d electrons. That was just a quick recap. Now on to metal complexes. Well, what actually is a metal complex? Well, a metal complex is a central metal atom or ion surrounded by ligands. They have different geometries. I'm just drawing one here known as the octahedral. However, I'm going to go through them in a slide or two time, and hopefully you'll be more familiar with them after that. But like I said, it's a central metal ion or atom surrounded by ligands. What actually is a ligand? Well, it's an ion or an atom or a molecule that can donate a pair of electrons to a central metal ion or atom forming a coordinate bond. You may be familiar with coordinate bonds from some of the earlier topics in chemistry such as AS, but just a quick reminder, all it is, if we take ammonia, NH3, got a lone pair and we can donate it to something, I'm going to call it a metal, the whole lone pair from the nitrogen forms the bond. So you know each covalent bond like this has 2 electrons, both are coming from the nitrogen. Whereas you have something like HCl, you've got 1 from the hydrogen, 1 from the chlorine, right? So it's not a covalent bond because there's 1 from, not a coordinate bond as there's 1 from each, but it is a covalent bond. Okay, bit of terminology now. Monodentate, bidentate, and multidentate. Well, monodentate has the word mono in front. Mono means 1, right? What this means is you have a molecule just like this here that's only forming 1 coordinate bond. Another one would be the Cl-, a lone pair on there, can form 1 coordinate bond with the metal. To further illustrate this, say bidentate, we'll look at some of the difference between mono and bidentate ligands. Well, bi, such as bicycle, that's just the same as saying 2, right? So we have a ligand that can form 2 coordinate bonds. Traditionally, there's something called En, and it looks a bit like this. NH2, CH2, CH2, and NH2 again. Well, for those who are very observant or seen this before, you may notice that each nitrogen has a lone pair, so we have two lone pairs in this entire molecule. So what we can actually do is we can have this central metal here. We have NH2, NH2, and we've got our bridging carbons. I'm not going to draw them out. But each lone pair can form a coordinate bond to this metal. So we have two coordinate bonds to this metal, meaning it's bidentate. And the other bit of terminology you need to know is just simply multidentate, which you may be able to figure out by now. All it is a ligand that can do multiple coordinate bonds, 3 or more. Fantastic, so now I know what a complex actually is. Now let's look at some of the geometries that different complexes can take. First of all, we can have an octahedral complex. This looks just like the one I drew in the previous slide. And it's an octahedral because I should say I'm using L just to stand for ligand right now. It's an octahedral because if you had this in 3 dimensions and you drew lines between them and had faces between all the ligands and things like that, it would look like an octahedron. I'm sure if you Google an image, it will help quite a lot with that. But remember, this wedge bond means it's coming out of the page, while the dash bond means it's going behind. So in a way, if we were looking at this perfectly side on, would have something like this, right, where we've got the 2 ligands right there, as would be looking kind of, as these are in plane of each other, would be looking at just look like a straight line. Hopefully that's not too confusing, but that's how we draw an octahedral. I'm just going to give you a quick example of that. So we have an iron-ion, and I'm just going to use a bit more terminology here. We're going to have 6 aqua ligands, and the reason why I call them aqua ligands is because that's the IUPAC terminology. So it's a group of scientists who've decided we're going to call ligands made of water aqua. And the reason why I'm drawing it to the oxygen is because it's the oxygen atoms that are doing the coordinate bonds, right? So we wouldn't draw it to the hydrogen because the hydrogen isn't doing the coordinate bonds. Think about it. Water looks a bit like this with 2 lone pairs, right? So it's those lone pairs. Either one of them could be doing a coordinate bond to this center metal. You may ask, why is water not doing 2 coordinate bonds? Why is it not bidentate? Because it has 2 lone pairs. Well, you don't need to know this at A level. The reason is d orbitals, they have different shapes and things like that. It's just not in the correct position to do that. If you want to think of it like this as well, you've got your lone pair like that forming a coordinate bond, metal's up there. Well, this lone pair is kind of not even looking at the metal anyway, so it can't do that. Depends how you would like to think of it. Aqua ligands have a 0 charge, hence why an iron 2+, central ion, also the complex has a +2 charge. So that's octahedral. Let's talk about square planar. These have 4 ligands. Best way to think about this is just imagine an octahedral complex and you've just removed the 2 axial ligands. If you don't know what axial means, it's just simply the top and bottom ligands. So up and down is axial, while around the center, left and right is equatorial. So we have a square planar here. Just give you a nice example. It is cisplatin. Looks a bit like this. You've got 2 chlorido ligands, and yes, that's not me just being weird. I am actually calling them chlorido ligands because chlorido is the IUPAC name for Cl-, not chloride in this case. When, like I said, only when we're talking about ligands. Here we have NH3, that's known as an amine ligand. Might seem strange if you've never heard it called that before, but it is. Here we have platinum in a +2 oxidation state. How can we tell that? Well, this complex, as you can see, has got no charge. NH3 has no charge, so that doesn't affect it at all. However, Cl is actually Cl-. The chlorido ligand is just a chloride, which means it has a -1 charge. So we can go the overall complex, which is 0. We can -2, which is the 2 lots of chlorido ligands, and that equals our metal charge, right? So 0 - 2, sorry, is a minus our metal charge. So we've got -2 equals minus our metal charge. Therefore, we just rearrange it and say our metal charge is +2. Just the opposite, counterbalances it. So here we've got Fe2+. Well, the aqua ligands do nothing, so therefore our complex is also 2+. Now let's look at the final geometry. Our final geometry is tetrahedral. You're probably quite familiar with tetrahedral because things like methane, they have a tetrahedral arrangement, but I'll draw it out anyway. It just looks something like this, where I should have put around here, you may have a charge, just call it X, you may not have a charge. And if they don't have a charge, you don't have to put the brackets around, just like cisplatin here, but if it does, obviously you need to put the brackets around, square brackets. A nice example here is copper 2+ with 4 chlorido-ligands around in a tetrahedral arrangement, and that carries a 2- charge. Once again, we've got copper 2+ and 2 minus on each chlorido, so 4 times 2 minus. No, sorry, 1 minus. Make 1 minus on each chlorido, so we have a +2 on the copper. 4 times -1 is -4, to then give -2. That's where I'm getting confused. It would then give a -2 overall. One thing, you may be thinking, okay, tell me, why do we get square planar with 4 and why do we get tetrahedral with 4? Well, there's a reason for that. Cl- chlorido ligands are huge things, right? Cl-, and they have a nice negative charge on there. So if you try to cram 4 of them round, they're just going to bump into each other, they're going to have electric repulsion, steric interactions. You are not going to be able to fit 4 of them in a square planar geometry, and even worse yet, I never want to see anyone try to put 6 of them around in an octahedral. You just don't get that. They are way too big, way too charged. So sterics and electrostatic repulsion. Whereas something like aqua ligands or amine ligands here, they've got no charge and they're a lot smaller, so you can fit them round fine and you get nice square planar complexes like that. But never if you've got 4 of these will you get that. Never ever. Right, so that's some of the geometry. Let's just talk about some isomers. Well, there are 2 types of isomers you get. You get optical isomers, which I'm not going to talk much about, as this is just a brief introduction, and cis-trans isomers. The best way to talk about cis-trans, just a quick example, as you saw on the previous slides, is just cis and trans platen. So here we have our cisplatin. Why is it cis? Well, 2 Cls are next to each other, and the 2 NH3s are next to each other. So that's our cis. And let's look at our trans. If you remember from isomers before, trans just simply means opposite each other. Right, so we can draw it like this, and then we've got our ligands opposite each other as such. So trans. Okay. And like I said, that's all I'm going to say on isomers of complex ions. So let's just move on to a few colour changes. There are loads of colour changes out there, absolutely loads. I'm just going to talk about 3 of the core ones, 3 of the most common ones that you see across the exam boards. There may be more that you need to know, but I'm just going to talk about some of them. So we've got a copper 2+ complex with 6 aqua ligands. We react that with 4 lots of NH3, and we have that in equilibrium, right? It's always in equilibrium. It may be a 99.9% on one side, but these complexes are always in equilibrium. 4 H2O is given off. So you have this reaction, ligand substitution reaction. That's something you should remember. Ligand substitution, that's the name of it. And there's colours associated with this. So this copper complex here is pale blue. It's a pale blue solution. Whereas this amine and aqua complex is a dark blue solution. So imagine it going from something like sky blue on a bright sunny day all the way to a nice dark blue felt tip. That's the kind of difference that you see there. And if you've done experiments at sixth form, school, college, whatever you would like to call it, then you may have already seen this before and you know what I'm talking about. If you haven't, Google it. I'm sure there'll be some nice YouTube clips somewhere about it. Okay, so for our second reaction, we've got the same copper complex that we had before, hexa-aqua, so 6 aqua ligands, and we're reacting it with the 4 chlorido ligands, well, 4 lots of chloride before they come ligands, then they're chlorido. And as before, we can't put 6 Cls on there because they're too big and too much repulsion. But what we can do is replace all 6 and put 4 on there. And like I said before, that would be tetrahedral. Once again, we've got the same starting solution, pale blue, but we've got a different ending solution. And that one is yellow. Hopefully you can see that, but I wanted to write it in the colour that it is. Yellow. Some of you may be thinking, I've done this in the lab. I've done this as an experiment. It was green. Why are you saying it's yellow? Well, the thing is, because it's in equilibrium, depending on the conditions, you've got temperature, etc., etc., you can have, say, a 50-50, I don't know the exact ratio, but it could be a 50-50 split of both those complexes. And when you start mixing these complexes together, you get a lovely green colour, right? And that's your explanation for that. So I'm not going crazy yet. But, you know, there is actually green even though it's blue and yellow. So now we're going to have a different complex, chromium hexa-aqua chromium 3+. We're going to react that with 6 NH3, again in equilibrium, and we get hexaamine chromium 3 complex. 6 water molecules kicked out. We just got to balance that equation there. So what's the colours of these? So this is a nice ruby red colour, right? Quite hard to miss, quite hard to get it confused compared to something like that's pale blue. But we get that. And then our product is a lovely purple. Maybe you might get it confused between sort of the dark blue and the purple, you know, depending what light you hold it in or if you're colourblind, but that should be purple, while this one should be dark blue. That's it for my introduction to complex ions. I hope you enjoyed. I hope I didn't do too many bad puns at the start. Please share this with your friends, they may benefit from it as well, and don't forget to like and subscribe for more. Thank you.